Thank you. All right, we get the panelists. You guys can come up and take your seat here. So I'm really thrilled and excited to be a part of this panel. So this is our panel on artificial intelligence in space, some benefits and challenges. So I wanted to ask the question to everybody. Just sort of think to yourself, or yell it out loud if you want. But so, like, why are you at this conference? I mean, so the reason for me being at this conference, and I actually think if we all sit back and think about why we're at this conference, it's because we kind of want to kick the space industry in the pants a little bit. I mean, that's really, when people ask me, what is your research in a nutshell? I say I'm kicking the space industry in the pants. And that's because I think that if we all work together and get some of this technology and science out of journal articles and into the people's hands that can actually use them in space, then that means that we're going to have a much more accessible space industry. We're going to have a much more accessible program where we can get space assets into the hands of people that can actually use them, like Indigenous communities in the north or research groups in universities across Canada and around the world. And so when I take a look at the kinds of technology that's growing around us, like in the automotive industry, in the electronics industry, we see incredible things that are just becoming normal, everyday occurrences, like adaptive controllers, and especially like artificial intelligence. So artificial intelligence, we know, is everywhere. It's every time we pick up our phone that's learning something about us, whether that is creepy or not to you. It is learning, and we all benefit from that. I came here on, what day was it? I guess Monday in a Tesla cab, which told me that actually cab drivers must get paid more in Montreal than they do in Winnipeg, because I don't see any Teslas as cabs in Winnipeg. But so even the Tesla, that obviously had a lot of machine learning and artificial intelligence in it. But the question here is then, how do we do this in space? How do we find out ways in which we can incorporate artificial intelligence in a safe way and a useful way that allows us to improve access to space? And so I don't think that it will be much of a surprise that many in the space industry find this an absolutely ridiculous idea. This comes from people that have been working in the space industry for decades that are used to doing code reviews where they quite literally all stand around and read every single line of code and make sure that they get 100% code coverage and they know exactly what the spacecraft will do at every single point in time. I'm going to read for you right now a redacted email that I received from an official of a space agency, which I won't say which space agency, but I will say it's not the Canadian Space Agency. So let me just clear that right now. So I had, and this was not long ago, this was less than 4 years ago. Less than 4 years ago, I had a PhD candidate that was interested in doing some studies on artificial intelligence, and this was the email that we got. I was copied on it. Dear PhD candidate, I know that you are a fan of machine learning. However, we are going to have an operational mission, and I am very skeptical about the implementation of machine learning on a satellite. Your colleagues are working on the subject, but they only apply this method for data analysis on the ground. This cannot be implemented on a satellite, and in particular, I am sure that we will not do that for the redacted spaceflight mission. I would not mind exploring this field for a part of your thesis, but I would recommend that you not lock yourself into this objective, because otherwise everything will remain very academic and it will not be of any use for this mission at all, and me in particular. I therefore do not accept your main research goal because people might reject the proposal immediately since it is not considered realistic. And here's the best part. We cannot leave it up to a machine learning algorithm to switch the mode of a satellite that costs us as much as 1,000 single family homes. Let me know if I'm wrong. Best regards, Space Agency official. So I quite literally have that framed on my wall in my office at the University of Manitoba, because to me that epitomizes why this is so important for us. Because it's not that this is some scary thing, it's that we need to find ways to harness it. We need to find ways to use it appropriately, and that's what this fantastic panel is here for today. So I'm going to just take a second and introduce the panel, and then I'll let each one of them talk about themselves. So at the far end, we have Dr. Paul Grouchy, Director of AI at MDA. We then have Kelsey Doerksen, a PhD student in AI and machine learning at the University of Oxford. And then we have Dr. Andrew Macdonald, an AI specialist at Mission Control. So we'll just start, I guess, at the end there in that same order. So Paul, if you just want to introduce yourself.
So yeah, so my name is Paul Grouchy. I did my undergrad at Queen's University in mathematics and engineering. And after that, I went to the University of Toronto, UTIAS, so the University of Toronto Institute for Aerospace Studies, under Gabriel Dilatario, who I think many of you maybe know. I studied with him for many years, and during that time, I also sort of did exchanges at the Helsinki University of Technology, Tokyo Institute of Technology, and Cornell University under Hod Lipson. So I've been studying artificial intelligence since 2007, so that's 5 years before deep learning was even a thing. So I've been at it for a while. And then for my postdoc, I actually worked with MDA's sort of robotics and space operations department. I worked with them sort of part with UTIAS and part with MDA, and implemented a number of these algorithms on physical systems. And so that was really exciting for me. After that, I did a tour of the Toronto startup scene, applying AI to the health industry, the legal industry, and most recently, inference acceleration, so ASIC chips. And then I returned to MDA 4 months ago as their inaugural director of AI at the Robotics and Space Operations Division. I'm really happy to be here.
All right, thank you. Welcome, Paul. Kelsey.
Hi, everyone. So my name is Kelsey Doerksen. I'm at the University of Oxford currently studying artificial intelligence, but I'm also spending time at the NASA Jet Propulsion Lab on a visiting research stint down in Pasadena, working with the machine learning and instrument autonomy team. So I did my undergrad at Carleton University, the aerospace engineering program, space systems. Honestly, if you told me my job was going to be related to coding, like, no, I would never have expected that. But I ended up doing a master's in computer engineering at the University of Western Ontario, basically driven from the fact that I was very interested in learning how to write code, and I knew nothing about it, or very, very little about it. And I thought if I wanted to work in space and use my space system skills, that learning how to, these skills would be really important. And so during my master's, I spent time at NASA JPL with the machine learning team using AI and machine learning to assist with rover operations and terrain classification, these types of things. And I also spent time at the Paris Observatory in France doing machine learning classification for solar events. So basically these huge explosions on the surface of the sun, trying to detect those to help protect our satellites. The past 2 years, I was at Planet, which is an Earth observation company based in San Francisco. I was a satellite operator there for the past 2 years, which is a really, really cool job. I highly recommend any young people that are thinking, what do they want to do with their life? Operations is very cool. I would definitely recommend. And we were also doing machine learning there to assist with operations and help offload some of that work because we had such a large constellation of 200 plus satellites and a very small team of around 5 to 10 operators. We did rely on a lot of automation, and we were looking at exploring how we can use ML to also support that. And so now I'm at Oxford. I'm working on the concept of trying to enable scientific understanding from data science, so using AI to kind of harness the power of AI on board spacecraft, but also with space-based assets and space-based data to hopefully enable science discovery of things that maybe aren't previously revealed with traditional data analysis techniques. So very happy to be here.
All right, thanks, Kelsey. Andrew.
Good morning, Montreal. It's good to see everybody getting caffeinated on day 3, and good to start with a panel. So I work at Mission Control. I work with a small team whose purpose is essentially to address the last line of Phil's email. If I'm wrong, let me know. We're attempting to prove them wrong. My background is as a physicist, so I did a mathematical physics degree at the University of Waterloo, starting with large-scale Monte Carlo simulations before anybody would have called that machine learning. Then I did a PhD at the University of British Columbia, in part at IBM Research in the Bay Area, doing nanoscale spectroscopy. And that really led me down the path of computer vision, because there's a point there where you're counting individual molecules on surfaces. And if you do that by hand long enough, you're like, there must be a way that I can do this automatically as you sit there in graduate school. And from there, I actually worked in MDA Earth observation for a bit, and it turns out counting molecules in imaging spectroscopy on a surface is very similar to counting ships in a SAR image, or counting trees in a hyperspectral image, as long as you change the scale bars enough from 1 nanometer to a couple kilometers. And from there, we really looked at kind of the autonomy aspects in planetary exploration, where now you're looking at computer vision from a rover perspective, or from a satellite that's informing a rover. And so we really think that machine learning and current definition of artificial intelligence is enabling for what the plan is going forward for the next 20 years in space.
All right, thanks very much. So as you can see, we've got a fantastic panel, a lot of experience, a lot of different kinds of experience. And so I'm really hoping that we can have this a good discussion this morning. But also, I don't want to limit it to just the four of us. If any of you have comments as we go, I don't want this just to be a lecture from four people talking to all of you. So if there are comments that you would like to say, stand up at the mic, and we'll incorporate them as we go. So I'm going to start with one question, though, just to kind of get some things rolling. So I wondered if you could all talk a little bit about some examples of artificial intelligence that you've incorporated into your work that you've done, either at your organization or in your research. And so, Kelsey, maybe we'll start with you on that.
Sure. Yeah, so I can start with on the operational side. So like I mentioned, I was a satellite operator for a large constellation. We had about 150 to 200 satellites at any given time. And so that is a massive amount of data every single day that we're getting, not only from the imagery that the satellites are collecting, but also just from the telemetry of the spacecraft. So, things like from the power system to the onboard computer to thermal, all of these types of things. And so it's a lot of data for us to analyze on the ground as a small team. So what we were doing was using machine learning to try to identify anomalies on board so that we could be able to assist with sort of this on-orbit anomaly detection system. Because we had so many satellites, there was around 200, but they were all the same. They're CubeSats. So effectively, they're all using the exact same type of hardware. So this way we had like a really good data set in that we could train our model on 200 plus satellites and then test it on the new satellites that we were launching, or train a subset from one flock of satellites to another. So this was one way we were using machine learning. We weren't using it to make decisions without an operator's input, but we were using it to assist with an operator to be able to figure out, what sort of anomaly are we looking at, what subsystem should I deep dive more into, because again, we're getting maybe 40 to 50 gigabytes per downlink per satellite. Every satellite downlinks around every hour or two, and then you have 200 satellites every single day. So it starts to get sort of in that big data category. So we were using machine learning to be able to assess that telemetry and see if we had any sort of anomalies that we should look into a little bit more. So that was kind of on like a classification side. Most recently, though, at the NASA Jet Propulsion Lab, I'm working on the Scientific Understanding from Data Science initiative. So what we're doing is we're partnering the machine learning group with the science teams. So we're working with atmospheric physics teams based on Earth atmosphere. I know we've been talking about Mars atmosphere as well this week, so talking about this planet this time. And what we're trying to do is understand the global drivers of climate change. The biggest challenge we have right now is the data is quite sparse in terms of our ground truth. So we have different stations based in North America, in Europe, as well as in East Asia, but that doesn't cover the entire globe. And so what we're trying to do is understand how we could train a machine learning model on these Earth observation data sets that can be used globally, and to basically understand what are the global drivers of climate change using these space-based data sets. So these are kind of the two projects I've been working on or have worked on in the past. I'm very much a proponent of trying to communicate with the scientists and understand what their needs are. I think there's definitely a big disconnect between very hardcore computer scientists and people that want to just do biology or chemistry or these other types of science. So I'm trying to kind of bridge that gap so that I'm understanding what their needs are, and is it machine learning, is it AI, because it might not always be. So that's kind of my goal with my projects, is to really connect with the scientists and understand what their data set is, what they're trying to achieve, and is machine learning interpretable enough for them to be able to use this different resource.
Yeah, thanks, Kelsey. I think that's been a common theme that we've heard quite a bit this week, is this intersection between science and engineering. And I think artificial intelligence provides a really important bridge for that we're seeing more and more often, is that we can, computer scientists can say, hey, I've got this really interesting tool I can find, like I think Andrew mentioned, I can find molecules, or I could find ships, or I could find whales, or I could find icebergs, or I could find something like that. And then let's try to find ways to work with scientists to understand, is that useful? And if it is, how can we tweak it in order to help our science? Because at the end of the day, it really is the reason why our space industry exists, is to support science. It's to support the scientists that are trying to answer important questions about this planet and other ones. So I think that's a really good point. Thanks, Kelsey. Paul.
Sure, yeah. So maybe I'll start with a terrestrial application from my postdoc that I'm quite proud of. there was a security robot that we were working on, and the operator, so it was manually driven with remote control. The operators sort of have a camera on the front, but when they get to a staircase, they're looking sort of right at the staircase. And so they need the ability to actually climb that staircase, and they can't do it because they have just no situational awareness once they get there. And so there's this task of maybe trying to automate this, see if you can push a button and then the robot sort of climbs the staircase. And it's a tracked robot, sort of those like a bomb disposal robot type of thing. And so we ended up building this simulation world that reminded me a lot of Inception, where there was just all these different staircases, and this robot was just driving and falling off the stairs and driving and falling off the stairs. And you just varied the parameters of the stairs so that it learns more generally how to solve these problems. And over time, we just left this thing running, falling down the stairs over and over and over again. Not in reality, because these are expensive robots, but in simulation. And then it sort of learned over time how to actually accomplish this. And then we actually ended up building this huge sort of kind of wooden structure that we could then, with pulleys and hook a rope to an actual robot. And it's still there, actually, in the staircases of MD8. It's near my current office, actually, so it reminds me of this project. And the damage we did to the walls is actually still there as well. But this robot, actually, we were able to port what we learned in simulation onto the actual hardware, and you could actually push a button, and it would go up the staircase. And what it was only using sort of internal sensors. It had no sort of external-looking vision sensors, only just based on IMUs. And for free, what you guys could also go down the staircase, because all it really learned to do was to stay straight on the staircase. And so this was an early example of being able to port stuff from simulation to the hardware. And this is one of the key challenges, I think, of AI in space, is taking something from simulation where you have to train these things because the systems aren't yet in their real environment, and porting that to the real environment. More recently, the Canadarm3 project is in phase B, so it's in sort of the technical design phase. And some of the challenges there that we're looking at are worksite surveyor and clearance monitor. So these are sort of when you're actually doing an operation, the idea is to have quite a high level of autonomy on Gateway, and in particular on Canadarm3. So the idea is you've got a plan and you want to execute that plan, but you want to make sure that your expected sort of work site doesn't have any unexpected debris in there. Maybe an astronaut left something lying around, or maybe a cable has floated in. And so you want to be able to, in real time, monitor using computer vision what is happening and what is in the way and what's there and what shouldn't be there. And the same thing goes for sort of clearance monitor. So are you staying away from other structures as you move and execute? And beyond that, there's also pose estimation, which is a more broad challenge, but also one that we're looking at for C3. So how do we determine if a free-flying object is prepared, if it's got targets on it? That's one thing, but there's also unprepared objects, sort of for satellite servicing, where the plan wasn't ever to service this satellite, but all of a sudden it's actually cheaper to go up and service it than it is to build a new one. And so there's a lot of interesting problems there that we're looking at solving about how to estimate. You need a high degree of accuracy to be able to actually grab onto these things and service them. So a lot of really interesting problems coming up that we're all very excited to try and tackle.
Yeah, thanks, Paul. In the talks that I've heard this week, I've heard a lot of people talking about some pretty ingenious ways to sort of pre-train some of these machine learning and artificial intelligence algorithms to avoid what you're talking about, right? Saying, well, we need to collect a whole lot of data. We just don't have the time to stand around or the money to let robots crash off stairs thousands of times before it can learn. And so there's been a lot of interesting things of people that have been incorporating pre-known dynamics into neural networks and finding ways to accelerate that learning so that we don't have to wait years or through thousands of robots. So thanks for that, Paul. Andrew.
Yeah, so I think that those are two really good pieces I want to latch onto. The first is what Kelsey said about if you don't take the end user into account when you're looking at putting AI into a space system, then you're kind of missing the point. Like, nobody's ever going to write a requirement for a space system that says must have AI. There's a functional reason why you need a certain level of autonomy, whether that's you want to go through 11 kilometers of ice on Europa, or for Canadarm3, like Paul said, the autonomy need comes from bandwidth constraints and other constraints that are inherent to the mission. And I think that AI itself is a slippery term. It's been around roughly 70 years, but both the artificial part and the intelligence part are hard to define. And when you put them together, they don't get any easier to define. So I think when working on AI in space, that functional definition of we want a system that can adapt to changing goals and priorities, that can learn from its environment, and can make decisions based on limited perceptive data that are good and that we can trust and that won't jeopardize the system are all key to actually building artificial intelligence on board. or downstream when you're processing huge amounts of data. And so kind of the two most operational projects that we have at Mission Control started with the science end users, which in our case for rovers are planetary geologists. And so what we have is a artificial intelligence convolutional neural network that does semantic segmentation of rover imagery into relevant geological categories. And that's been built up through funding with the CSA and deployed in analog missions in Iceland, and is now on board the iSpace lander that's launching hopefully this month on a Falcon rocket as part of the first commercial mission to the moon, as a capability demonstration of what you can do once you have one of these systems processing sensor data where it is. And our other project is on an ESA satellite that's already in orbit called OPSAT that ESA's put up there with the intent of trying new methods and technologies on board satellites. And what we're doing there is actually hybridizing a neural network that's already on board, running on a system on a chip CPU, and we're trying to make it more efficient by putting parts of it on an FPGA, because as Paul knows, trying to run large-scale neural network, even inference, on flight hardware is very difficult because you just don't have the memory and power requirements that you need. But at the same time, you can still do things that are useful. So if you're taking a picture that's oversaturated because it's all cloud, then you don't necessarily need to use your limited downlink to actually send that to the Earth unless you're studying atmospheric science. And so the ability to add that perception on board grants you more autonomy, which actually lets your human, because it's kind of a human AI team, focus on what's important in the downstream application.
Yeah, thanks for that. So obviously, as we've seen here, contrary to the email that I got, we have so far been quite successful in doing some of this. And actually, I'd be remiss if I didn't point out that these are not also the first that has happened too. So even funded by the Canadian Space Agency and European Space Agency, many of you know Jean de La Fontaine from NGC has been doing quite a bit of work as well on the probe missions as well in terms of artificial intelligence and autonomous fault monitoring. So when we think about that email, though, when we think about what's happening in space, maybe some of us can think about some of these challenges. So obviously, one of the challenges is just inertia, just trying to get people to accept this technology and understand that it can be safe. But I think there are other technical challenges and other things that get in the way when we try to do this. And maybe some of those challenges turn into opportunities that allow artificial intelligence to do better things and more intelligent things than we have been doing in the past. So maybe I'll see if our panel can talk to some of that. And Paul, we'll start with you.
Yeah, so on the challenges side, there's three. I think we've alluded to all three of them already. The first one is one that I'm focused quite heavily on right now, which is, I call it domain adaptation, but it has a number of different, you can say sim to real, reality gap, domain gap. But this is sort of what I've already discussed, is we don't have representative cameras in space yet for these new missions. We don't have this data, but these algorithms are really data hungry. And they're also somewhat sensitive to the data. So if you train on a one domain, so in a simulation, and then you transfer to another domain, these models can actually be quite sensitive and can really lose their power in this new domain. And so this is a grand challenge, both in computer vision, but also even just on the sort of robotic simulation side, the physics of the robot, when you're dealing with really low tolerances, these things actually matter. And so you need high fidelity simulations for the physics and for the dynamics of the robots, but you also need really realistic imagery or interesting techniques to get around the lack of realistic imagery to be able to train these models for space. So this is one of the big challenges. The second one, as again was also alluded to, is sort of V&V, the testing of all these, and convincing people, especially when there's humans up there with your systems, convincing everyone that this is safe, that this is going to work, and it's not going to fail catastrophically. This is a big deal, and it's in many ways it follows the same things that have been done for the last 30 plus years, but in many ways it's different, and we need to sort of acknowledge that and come together to figure out what it is that we're going to do to assure ourselves, and there are a lot of ways of doing that. And lastly, it's the compute. The compute's a huge one. As Andrew mentioned, even inference, which is just sort of running the model, is very difficult in today's compute up there. And even for C3, there's going to be more advanced compute, but it's still going to be 5-10 years behind what's available on Earth, and that's not going to change just because of the the environment of space. And then we want to think about, adaptation, and adaptation is maybe training. So this is, again, way more compute intensive than just inference. So there's a number of challenges there. And thankfully, all of these challenges, especially sort of domain adaptation and the compute, are being solved for different reasons on Earth. There's edge AI for your phones and for all these different devices. Domain adaptation is a big problem for autonomous vehicles. They need a ton of data for this sort of thing, and they have some from driving around, but it's never enough. These things are very compute hungry, and so there are techniques available that are being developed that we can hopefully translate to space. And the opportunities are as discussed. We can hopefully streamline ops, do a lot more with a lot less communication bandwidth, and really push the envelope of what's possible.
So I'm actually going to ask you a bit of a follow-up to that, Paul, because I think you touched on something really interesting, which is that other Earth-based applications are doing similar things that are applicable in space. So when you hear about an Earth-based application, and then you go to your space colleagues and say, hey, someone's doing this on a Tesla, or someone's doing this we're doing it on our phone right now, how do you spacify that? Like, how do you take that and turn it into something that is understood by the language of all that's sitting here? Sorry, and you also hit on verification and validation, which are two words that we all understand quite a lot in the space industry. So how do you cross that boundary between what you would do on a phone and what you do on a satellite?
That's a very good question. A lot of it is sort of just education, I think, and discussing things just honestly, and highlighting. It's a lot of the challenge is that it's an unknown for a lot of people. They've been working on this sort of these processes that have been proven over the last 30 years and are very well understood and very well known. And they hear something, a neural network or AI, and the thought is that it's this black box, and we have no idea what it's going to do, and it's going to go off and do horrible things in space. But the reality is it's not a black box. It's actually what's called a white box. You can actually see every single parameter, and you can actually characterize the thing if you really want. You can reverse engineer it into something that's human readable. It is actually deterministic for inference, so the same inputs will give you the same outputs 100% of the time. And these are sort of the education sort of processes that you have to go through to acknowledge people's concerns. They're all very valid, but also just to highlight that it's not quite as scary as it's made out to be. And machine learning isn't just neural networks, by the way. Machine learning is linear regression, logistic regression, symbolic regression, where you get equations out is your answer, which are human readable. Decision trees, which are also human readable. So there's a number of ways to say, guess what? It's not quite as scary as you might think, and it's not as unknown, and it's not this black box necessarily. So that kind of touches on both V&V and your conversations you have with people in the industry.
Yeah, I sometimes wonder if 2001 Space Odyssey and our good friend Hal actually did us a huge disservice by making all of public terrified about what AI can do in space, and now we're still recovering from that movie decades later. Kelsey.
Yeah, thanks. Honestly, every time I tell someone I'm in AI, it's either HAL comes up or Terminator. It's one of the two. They ask me. So yeah, I think it is what it is. But I mean, I loved what you said about the communication and that it's not a black box or trying to communicate what exactly the model is doing. This is a lot of what I'm doing right now. I'm working with Earth observation data sets to predict landslides in Nepal. And we're trying to then implement this and have it as an early preparedness and disaster response for the Nepalese government. And so it's really trying to make sure that we are able to effectively communicate what exactly the model is doing and what the output is, because they don't really need this super highly complicated model output that this is how many nodes I had and my UNet is this deep. They need to have a map, a binary map of Nepal, and show where did the landslide occur, where is it not occurring. So I think that's one thing too, just goes back to the communication. That is a challenge, I think, regardless of your application, whether it be Earth-based, on Mars, on the Moon, whoever your stakeholders are, I think the communication is major. And this is not just in the space industry, this is across any industry, but that's always a big challenge. Something else I'm working on, and that we're also working on at JPL, is uncertainty quantification. So essentially what it means is you want to know what your model doesn't know. So take the example, this is not a space example, but take the example of classifying between pictures of dogs and cats. Okay, you're training a model, you give it a bunch of dogs, you get a bunch of pictures of cats, and then hopefully when you give it a new picture of a cat or dog, it can tell you, yes, that is a cat, or no, that is a dog, etc. But what if you give it a picture of a turtle? it shouldn't tell me that this is a cat or a dog. It should tell me, oh, actually, I've never seen this before. This data is totally out of distribution. And it shouldn't be very confident in its prediction. So this is what we're trying to do in space-based applications, and this can be even from making decisions in terms of which way your rover should turn on Mars, if it should go straight, and getting feedback in terms of how certain it is that it actually truly did the operation that you intended it to do. And we're also using this, again, for the air quality assessment and global air quality assessment, basically creating this map of the entire Earth. And each pixel that we have at different resolution gives us, an air quality assessment, gives us a measurement. But we also want to know like how certain we are that that measurement is true, because this is going to affect policy decisions for governments. If we're saying like, hey, your air quality is really, really poor, and we've ingested roadmaps as part of our data, and this is showing us that from 2000 to 2020 that the air quality is like drastically gotten worse. This is actually making real change on Earth. That's the goal anyways. So this is a big challenge, not just in the Earth observation sector, but I think just across the space sector in general, is trying to make sure that your model understands its data distribution and when things are out of distribution. This can be used for space exploration projects as well, a lot with computer vision. But it's a big challenge trying to figure out what your model is doing and how it is quantifying its uncertainty. Because again, it could tell me that my turtle is with 100% confidence a cat, but this might not actually be the case. So this is a big challenge that we're trying to work on.
Yeah, I think that is so critical. This idea of confidence, and I actually think that's an area that allows us to cross over between computer science and engineering, because we're all quite familiar, especially those of us in the room that are into guidance, navigation, and control. We talk about confidence all the time. We talk about probabilities. We talk about covariance bounds and matrices. And I also think it's applicable when we start talking about risk tolerance, right? I mean, a lot of us say, and you'll hear Rob Z from UTIA say all the time, what we need in the space agency is a better tolerance to risk. But then you go to the space agency and say, hey, I'm going to build you a risky spacecraft. They're like, yeah, no thanks. I don't really want to do that, right? But if you could say, well, how risky, right? So we all agree that we can accept a little bit more risk tolerance on, say, a CubeSat and a lot less risk on something like RCM. But what does that dial look like? And how do we evaluate that tolerance? How do we evaluate that confidence in our system? And I think what you bring up is really critical, because at the end of the day, we need to sit down and verify these systems, and we need to be able to say how confident we are that this system is going to work. And so I think knowing how well that system works is absolutely critical. So I think that's a great point. Andrew.
Yeah, it's not just the risk dial, right? If given just the choice, would you like more risk? The answer is no. I mean, it's a multivariate optimization, right? It's how much more capability am I getting per unit risk? So what can I do that I need to do, and how much risk does that add? And I think that Kelsey and Paul already covered this question really well. In particular, I love the white box explanation, because that black box thing is something I push back on, because all you have to do is talk to a pharmacologist to get a real black box. Like if you want something that affects human safety factors, then try developing a new drug, because you will not be able to take it apart like a neural network and see the inputs and outputs at every single step. And so we already have fields of scientific research where we are able to trust systems that we can't fully take apart and put back together. It's just that that's a relatively new paradigm for computer science, especially for software engineering in space. And so because a lot of these models are based off huge statistical distributions, what we have to understand is that it might not be possible to fully cover every single edge case in the way you could with traditional software. And so you need some amount of certain uncertainty quantification, some amount of explainability, and an understanding of the biases in your data, in your training data. Because, as you said, when you want to spacify one of these things, one of the great things is because everything is so contingent on data, a lot of the architectures are being just freely published by the world-leading computer science groups. Then you have to figure out how to train them and do the domain adaptation within the space context and figure out, okay, when it identifies this turtle as a very confident cat, what happens to my system? And that's interesting. And in particular, when you get to the point where you're not just doing passive computer vision, where you might actually have a rover where you're going to intervene, you're going to pick up a rock and, say, target it, you're actually going to shift that underlying distribution. And what happens then? And there are examples of this. So ChemCam on Curiosity, on Mars, Curiosity, can autonomously pick targets for its laser-induced breakdown spectrometer. And to do that, they had to build a whole safety system on top of the safety system that was already there in the software for the libs, so that the optics never point at the sun, and so that they never point the laser at part of Curiosity and fire it into its wheel. But that's been done, at least to an extent, and you can certainly see as we put more rovers on the moon, or just more spacecraft in general, a need to scale that up.
Yeah, I think that's fascinating. We're starting to see that a lot more and more now in terms of what we can do to keep software safe, or keep systems safe so that they don't bring down the entire system. I mean, for decades, centuries even, we've been talking about ways to prevent faults from extending to different parts of the system. How do we firewall certain areas off? And I'll just actually bring up a little anecdote. So I spent a little bit of time between my space systems career and becoming a professor. I spent a little stint in the drone industry. And so as you can imagine, the drone industry is also sort of colliding a little bit with the human aircraft industry, and trying to answer questions, not only how do they coexist, but when we start having things that are flying that are not necessarily approved in the same rigorous manner as human-powered aircraft are, there were a lot of questions. And so I can remember having some early conversations with Transport Canada and the FAA about saying, well, normally we certify all of our software to this very strict military requirement. How do we do that now with an open source autopilot that's stuck on the back of a DJI quadcopter? And how do we justify that being in the same airspace as a Boeing 737? And so what the FAA came up with, and has been adopted by Transport Canada, is something known as SOUP, or Software of Unknown Pedigree. And they now have an entire standard written around how do you firewall off a certain function of software. How do you monitor that software and make sure that it's not going to go out of bounds? How do you make sure that it's not going to misidentify a turtle as a cat? And if it does, how do you make sure that you don't treat this turtle like a cat? Which I don't quite know how you do that, but I think you know what I mean. So what's interesting now is that people are starting to look, as you mentioned, about, well, how do we do that same kind of thing in space, and can we integrate this into our verification and validation programs? And I think it's a fascinating question. I'd like to take a minute and just ask the audience here: have any of you had challenges, successes, things that you've tried that worked phenomenally well, things that you tried that have not worked well? Have you run into these barriers that we're talking about, where you've tried to pose a machine learning or artificial intelligence question to the space industry and have them laugh you out of the room, or maybe they welcomed it with open arms? Please.
So maybe first off, just kudos to CASI for putting such an awesome panel together. So my question, maybe to set the scene a bit, I think I'm kind of on the fringe. If we were at a dance party, I'm kind of on the sidelines watching it all, maybe rocking to the beat a bit. But you're on the dance floor. Some of my experiences, and maybe in the context of sim to real, and in a computer vision context, I kind of have this sense, particularly when we're talking about space, that we're kind of it's a huge challenge because of obviously the logistics involved. And sometimes I feel that we're slinging infants into space, and we got to watch them grow, and eventually they'll get there. And then at that point, we can kind of harness some of the value that we're hoping for. But in my experience so far, that sim to real challenge has been really challenging, just because of some of the physical and logistical constraints. And so maybe my question, as you're on the dance floor now and you're really in it, is that kind of gut perception, will that be overcome? Will we get to a point where we're actually maybe fielding those capabilities on day one? Or do we think that there is going to be a kind of a persistent challenge where we've got this, let's say, beta capacity or capability, and now we're getting the real data. Now we're able to recreate the inference, then put into operations. Like, can you give me a sense of will we always really have that constraint and have to find whether it's maybe Pathfinder missions or just that natural state that we've got to kind of let things organically grow, and now we can kind of move them into formal operations because we retrained that model with real data, and now we're really in that point where we can kind of formalize, that vision of what we wanted that system to do.
Yeah, that's fantastic. Anybody from the panel want to take that on? That's a great question.
I can start on that one.
Sure.
So I think a couple of things are going to happen. So the lack of data leads to certain really need for simulations, or in our case, we have a 4,000 square foot lunar analog facility called the Moonyard, where we're getting most of our training data because we feel that we can do a better job there than in a full simulation environment. We're going to see in the lunar surface cases more cameras on the lunar surface that aren't from the Apollo era, and suddenly we will have access to data, and so we'll be able to rely a little bit less on simulation. The problem, I think, this isn't a problem. Eventually, if these capabilities become mainstream, we'll stop calling them artificial intelligence, and they'll just be accepted, and something else will become the new thing that we're trying to solve. So I think there'll always be a pipeline of new technologies that we're trying to characterize. But I think we will add capability, particularly in the short term. And for certain missions, that gap, like C3, it's just inherent. Like, there's no starter C3 that's halfway between ISS and the gateway. It's just going to have to be operational when it gets there to some minimum requirement. And maybe that's added capability by 2035. And so that's certainly part of it, I think, is the direction we're going.
Does anyone else have anything you want to add to that?
Yeah, I totally agree. I mean, even just from talking to some other colleagues here that do satellite operations on RCM or very, very expensive spacecraft versus me who is operating CubeSats, which are relatively cheap. For us, when I was operating, machine learning was a little bit easier to integrate into the operations community at my job because it wasn't like that big of a deal if one satellite went down for an hour or 2 hours or even 24 hours because we had 150 others and we knew we were launching 40 in another 6 months type of thing. So I think with the rise of cheaper, quote unquote cheaper, it's not cheap, but spacecraft, especially with CubeSats, we can gather data a lot more quickly and then we can then implement AI on board almost right away because your overall cost of your mission is not going to fail just because 1 or 2 satellites out of a constellation of 200 aren't working properly. I think that's maybe where it will go, and then in terms of like them propagating to the rest of the entire constellation, we'll go from there. But I think now because especially satellite constellations are just, I feel like everyone has a satellite constellation nowadays. They're just getting they're very, very popular, and especially with CubeSats, I think this can be a way to kind of less risk cost or less financial risk to test things on CubeSats that can then be implemented into other constellations or other more expensive spacecraft. That's at least where I see from the operations perspective.
Yeah. Did you have anything to add about that too, Paul?
Yeah. I'm very optimistic that we're going to get around this problem. But to be fair, I also told my wife 10 years ago that self-driving cars were 5 years away. So, let's take that with a grain of salt. But yeah, I'm an optimist for sure. But it is the self-driving cars. Google's working on this problem. The biggest labs in the world are working on solving these problems. And so I do think there are results around the corner that are going to get us through this. And deep learning and machine learning has benefited a lot from the gaming industry. They pushed the hardware forward. Deep learning only happened because GPUs were built out in such a way that then all of a sudden it became almost trivial to train a neural network, whereas before that on a CPU it was next to impossible, and that was the gaming industry. And now gaming industry has also pushed forward the simulations. So there's these new graphics engines, gaming engines like Unreal Engine 5, for example, that are hyper realistic. And you can tweak the lighting, and you can tweak the camera parameters, you can tweak everything you want. And so there actually is now hyper-realistic simulation capabilities that we can do on Earth. And then you can apply sort of these techniques from the literature on top of that. So one approach is to just add noise across a wide spectrum of potential cases. And so the hope is that whatever you see in the real world is within that spectrum that you've trained on. So the network is very general in terms of what it can handle. And there's other techniques where the model is actually in the loop and you can actually train the data generator. So you generate some data, you train a model, you test on a small amount of real data, and you can backprop all the way through to the original data generator. So you can actually learn how to generate data that's going to train a model on simulated data that will translate to real data. So some really interesting techniques that are coming up, and so I am optimistic that these problems will be solved. And there is also always a commissioning phase, right? You get somewhere new, you turn your cameras on, and all of a sudden you have that data that you need. And if we can get the compute to where it needs to be, maybe we can even do the last leg, that last little bit of training on the actual system. So I'm optimistic.
So how does that make you feel? Like, are you optimistic, or are you as nervous as maybe some of the other people, possibly in this room, that are like, I don't know about this in space?
No, I think I'm optimistic. I think to Paul, your last point there about, commissioning phase, right? I think it's kind of re-looking at that and looking at the sense that, okay, this is going to take a little bit extra in the interim. This is that last mile that we need to get through. I am optimistic, but I also, feel out of my depth a lot. And these are big challenges, and the only way I can see it, in a sense, is real data. But to your points about where simulation's going, where models going, yeah, if you can, if we get to that point, and I think the compute piece as well, the sense is that, these things are going to be in that last mile compute that's sufficient up there, taking it across the finish line. I think it's all very possible, but also that added complexity and challenge to bring it all together. But once it is, I mean, these are groundbreaking things.
Right.
Whether it's autonomous flight dynamics or extracting value from data, not necessarily sending all the data down and sending the information in from a high TCPET cycle. Like these are very paradigm shifting things. So very much worth the complexity and challenge, but also totally terrifying when
Totally.
as I said, on the fringe of the dance, I don't understand the dance fully, and meanwhile, everyone's getting down. So.
But I think that's maybe part of the barrier here, right? Is that to some extent we can all sort of understand that, we got a honeycomb panel and we got to make sure it doesn't break. Or we got a computer that has to add numbers together. Or we have an attitude control system that has to point. But when we got this black box that's doing magical mathematics, that's coming up with answers, we're all kind of a little bit afraid of it, right? And so I think even that statement of kind of like, this isn't my dance, I don't want to touch it, or like, I hope the experts know what they're doing so that I can just approve it. I think that's something that we need to kind of work on, right? We need to try to make this be a little more accessible, like a honeycomb panel, that we can all sort of sit back and understand and say, that feels pretty stiff. But I think you also brought up another good point, and that is one of operations, right? So like, how do we incorporate artificial intelligence into operations? And actually, sorry, I see you're standing here too. Do you have a comment you wanted to make? Oh, sure, yeah. Let's dive into that for a minute. Please, go ahead.
So I also definitely don't necessarily know my AI systems, but I do know more of the systems engineering, the VIV, and so I'm very fascinated on, you're talking about the uncertainty quantification, sort of the VNV process. That's not really a black box, it's more of a white box, and so I guess I'm interested on how we go through of like, okay, you're doing this VNV process, do we know, or are we able to determine sort of failure modes? Are we able to go work back and say, oh, we know that it would work in this case, but this image would cause it to fail? And you talked about maybe giving it an image, but is there a way to work back of saying, well, we don't know what the image is, but if we do this process on the white box, well, that gives us our failure image? Or other ways that we can determine what those failure modes are, or try to quantify those failure modes and try to know when robust is robust enough.
Yeah, does anybody want to tackle that? I think that's a great point.
Yeah, I can go ahead. So I think one way that we do it in terms of like traditional classification, especially with imagery, is data augmentation. So say you have digits 1 to 9, or 0 to 9. This is the MNIST data set. For those of you who are familiar with machine learning AI, it's used a lot for training and testing different things. And you can do data augmentation, like maybe I'll flip my image, maybe I'll add noise, like Paul was saying, or you can even give it a fake label. So I could label my 3 as a 6 and see how my model, if I'm training a few of my 3s are actually labeled 6s, and then I give it a new 3, what is my model going to actually output? What is it going to tell me? So data augmentation, I think, is a great way where we can kind of mess up our data a little bit and see how our model responds to it, and then you can also quantify the model's uncertainty or what its confidence threshold is based on, sorry, I'm getting a little deep here, based on the entropy that it's that it's measuring based on that set of threes or that set of digits. So data augmentation is definitely a way that we're doing things right now to see how robust our algorithm is to these types of different anomalies that we're seeing. Maybe we've never seen this image before, and we're trying to make our model more robust to it with that.
So how do we incorporate that robustness? How do we incorporate that verification and validation into actual operational scenarios? Like when we start to think about artificial intelligence in, say, operations, Kelsey, you've talked about this already, about some of the early operational changes that you've been able to see at Planet because of artificial intelligence. What are some other ways in which operations are being affected, or even assembly, integration, and test? Like how is this being changed today thanks to artificial intelligence? Maybe Andrew, we'll start with you on that one.
Yeah, so I want to kind of flip the script a little bit on the idea that adding AI to the system always makes it riskier, because there is a paradigm where adding it actually makes it safer, because you're able to perceive threats that you wouldn't otherwise, and you're able to get those to a human decision maker faster than you would otherwise. So you can get blindsided in the current paradigm but because your software is closed to a fixed number of inputs, that's the only thing it's able to consider because it can't learn on mission. And so I think in operations, there's the possibility to get way more real-time feedback faster and be adaptive to it, whether that's a satellite operator or a rover operator. Even though we haven't yet, I would say, if you look at the NASA Systems Engineering Handbook, there's no section on like, okay, this is how you V&V your learning software. It's a little bit like in the 90s, the idea of a rocket landing is utterly ridiculous. And now I have like friends with their kids who watch like an Atlas launch, and then the kid's like, okay, we got to wait for it to land, and their parents are like, that doesn't happen to all rockets. And it's a similar paradigm with, I think if you never really adopted the software that learns, then if you grow up with that, it's very different. And kind of with the V&V for MoonNet, this neural network we're deploying to the moon, we've done things like domain adaptation, augmentations, robustness, and you hold back certain data that you think is going to break it, and you see what its outputs are. Now, one of the interesting things is it's just a combinatorically hard problem, because if you look at a sensor, any sensor, then the number of options for your inputs is the number of pixels multiplied by the bit depth, which is huge even for a really small camera. And so it's actually not feasible to test every single possible input, but you need to know how certain families of inputs will respond, and that you can test.
That's interesting. Yeah. Kelsey, I know you've talked a little bit about some of this. Yeah.
I totally agree. It's really hard to test for everything because, again, we don't know what we're going to find on certain planets, or we have an idea. Based on orbiters that we have, we know, kind of the idea of what the Martian regolith is made up of what the lunar regolith is made up of. But we're now starting to explore areas of planetary bodies that we've never seen before, whether that be with satellites or with humans on the moon, now with rovers. So it's really just a matter of trying to figure out how we can make our model as robust as possible, but also keeping humans in a loop, I think, is a very key point that Andrew made. We don't need to have, at least I don't think at this point, our AI making every single decision and giving it life-ending or mission-ending abilities. I don't think that's really the goal in a lot of these exploratory missions. At the end of the day, Phil said this, where a lot of us are here because we love science. I think that's like space exploration is interesting because of the science we can get back from it. And so that's what we're trying to do with AI, especially onboard rovers and satellites and things like that, is to kind of enable this science. And so it's really just trying to make the science happen faster. At least that's what I'm really interested in myself as well. Like, let's get as much science back as we can. We know it takes years to even build these spacecraft, to test them, to get them to Mars, to get them to the moon. Hundreds of people are involved in every single mission, and then people are operating rovers for 15 years, 10 years at a time. Like, it's a really long time. There's a lot of human effort in it. So if we make it like a little bit easier with AI, that would be nice, especially with what data should we send back, and trying to make our model more robust so that it's not, again, sending back like cloudy images. Sorry, atmospheric scientists. Or images of like the rover leg when we don't really care about that. I think that's what is going to be kind of the next step and where we're going. And again, not completely cutting out operators. I was an operator. I love operations. It's more trying to support them, I think, is a key here.
Yeah, I think that's important, is that a lot of people sort of think we're going to flip the switch one day and all of a sudden everything is going to be run by robots and it's going to be run by computers and we're going to have nothing to do and we're all going to sit back and watch it. It's a little more gradual and it doesn't have to be all or nothing. I think that's a really good point. Paul?
Yeah, I mean, I don't want to sort of repeat everything. I'm in full agreement here. But it basically comes down to what we're seeing in the autonomous vehicles. And they have these levels, right? Level 1 autonomy, 2, 3, 4, and 5. And 0 is a car without any sort of autonomy whatsoever. But level 1 is just a suggestion. It's a blind spot monitor where the light comes on and says, hey, don't make this turn, don't change lanes or something in there, and that's a safety thing, like as Andrew's saying, like it's safer that way. But if you really want to, go ahead, drive into that car next to you. Like there's nothing there stopping you, and that's level 1 autonomy. And this is how we're going to start. We're going to start by making suggestions, by running things alongside the mission ops that are already there, that we're already confident in, that are already safe. And then we'll build trust. We'll build an understanding that these models are doing the right thing, and they will fail. The models will fail early. And then we can use that information to determine those failure modes, to figure out what is going wrong and why, and how can we make these systems better. And then we go to level 2, where we give them a small piece where they actually are doing a small bit of autonomy, but it's, again, in a human pipeline where humans do everything up until a point, there's a bit of autonomy, humans take that output, they check it, and they keep going. And then we keep going from there to level 3, which is conditional autonomy, where now we're talking about like adaptive cruise control, lane following, where you can take your hand off the wheel and read a newspaper when you're on the highway. And then eventually level 4, where then all of a sudden you are taking the steering wheel out of the car. So that's what we have to do. We have to build heritage. We have to build confidence alongside the current systems, not flip this switch and throw everyone for a loop, because that's just not going to work.
So do other people have some experience here? Yeah, please, Chris. Yeah.
Thanks very much. So this is a fascinating discussion on the interpretability and confidence and sensitivity to various inputs and all this kind of stuff. And I'm just curious, because in another domain that is actively used, so optimal control, let's say, right? I don't know how many of us can, interpret intuitively the inverse of a 10,000 by 10,000 matrix or something like that, right? But we use it, and one of the things that, like, the theory, there's underlying theory about, like, Lyapunov stability and that kind of stuff that allows us to trust it even though we can't interpret it. So I'm curious if there's work in AI towards something like that. Is that a pipe dream? Will it always be sort of statistical and there will always be some uncertainty because of the domain difference? Or is it possible to work towards something where, although we can't, know ahead of time exactly what it'll do, or okay, it's deterministic, but you know what I mean, like in an intuitive sense, but we can establish these sort of trust bounds because we know this for sure.
Yeah, I like that idea of boundedness, right? Because you brought up Lyapunov, and that's effectively what that is, right? Just saying, I don't really quite know what it's going to do, but it will stay bounded, and I know that for certain. So that's a good question for the panel here. What do you think in terms of bounding AI or bounding the outputs in some way to help gain confidence?
I think it's necessary. I mean, you have to bound it, at least for the foreseeable future, because you don't know. Basically, you have 2 sets of inputs and you get 2 sets of outputs. And if you interpolate between those 2 sets of inputs, you can't interpolate between those 2 sets of outputs. You might be in a completely different region of output space, and you won't know that until you see those inputs. And so you have to bound the output space so that it doesn't, as was could have mentioned previously by the other panelists, so that you don't go and do something you're not supposed to. But that being said, I want to come back to the fact that it's not just neural networks. Symbolic regression is an approach where you actually produce equations to fit your data. This is human readable. This is stuff you can apply the techniques that already exist on to gain that confidence. And so there are other approaches out there that are machine learning that learn from the data, but that produce a model that is fully interpretable given the current techniques out there.
Yeah, I totally agree. We use a lot of the time in science domains as well, like decision trees, like a random forest, which is just a set of decision trees. And you can get a feature importance out of this. So basically, you have maybe 100 features, so 100 different variables, whether it be like surface pressure or temperature or these types of things, depending on what your domain is. And your decision trees or random forest can actually give you a ranked feature importance of, out of all the features you have out of your feature space, these are the ones that were the most important in terms of me being able to make my prediction. This is a great way to, especially for science domains when you have these massive data sets, to be able to figure out like, oh, what is actually the most important variables that I should be maybe looking a bit more into that can sort of inform physical models as well. So yeah, there's also an area, I won't go into it because I think it's too complicated for even me to be able to explain it all correctly or give it any justice. But Bayesian deep learning, as well as like Gaussian processes, these are trying to, their outputs are probability distributions as opposed to like a single yes or no. So that's definitely an area that's being developed quite heavily at Oxford to be able to make our deep learning models more interpretable.
And then you can pair those models as well. So if you can impose a hard bound, like chem not staring at the sun, the reason you know why the sun is there is because of an astrophysical world model that applies to the real world. And one of the parallels that's made between symbolic AI that Paul mentioned and deep learning is it's kind of like type 1 and type 2 thinking systems in our brains, which is sometimes we perceive data and we're processing it based on statistics, and other times we kind of impose a world model on how things work, gravity, electromagnetism, physical sciences. And one of the kind of core things that's happening in the AI community right now is how to build in world models into deep learning so that we can establish a greater degree of trust. And there's been some interesting work on that with making random forests and neural networks interchangeable, or in very large language models, there's something called chain of thought prompting, which is you can ask a model with hundreds of billions of parameters question, and then you can prompt it for its chain of reasoning, how it arrived at that answer.
Interesting. So apparently what we also have happening in the room right now is a little bit of telepathy, because I was hoping that Armine would stand up and give us some examples of some of the work that GlobeVision has been doing. So Armine, please.
Thank you, Phil. My name is Armine from GlobeVision, a company in Montreal. What I would like to do is to share our experiences in this domain of AI. We started working with AI techniques since we started in 2003. And Canadian Space Agency gave us a project to look into RadarSat-1 telemetry data and see if we could find the faults when it happened to the first wheel of the spacecraft and it failed, and the second one did the same thing. So they gave us the data without giving us the engineering drawings or the models. And we did successfully find when it occurred, and then we shared with the operators, and they indeed validated that we found the problems or tried to identify the anomaly at the correct time, which was very exciting and encouraging. Ever since then, I have to say that whenever we went and we met another client saying that, we are using AI techniques, such as neural networks and all of that, they would say, it's a black box, and put an X on us, and they wouldn't want to get engaged with us. So we did change our approach. We said we are not doing AI, but we are doing CI. C standing for computational intelligence. Unfortunately, there are so many projects that we have, the title is CI, not the AI. And ever since then, we have developed so many operational solutions using AI techniques that currently they are in operation 24/7 in different industries, and it is proven to us that it works. But it needs a very special attention when it comes to an operational environment rather than a research environment. And currently, we are very fortunate that we are involved in a very big project, but that we are comparing the results of AI approaches with model-based or engineering concepts or the way we used to do this type of anomaly detections. And the challenge is that, to be honest with you, AI is not performing the way our well-known engineering models are performing. And now we have gone into creation of gray boxes, which are combination of physics-based and AI-based. So if you combine these two, you will have a better chance of providing solutions to the industry for the engineering systems that make up our satellites or aircrafts or all of this stuff. That's all I wanted to say, and good luck to all of you. We have a big job ahead of us to convince the industry to give a chance to this type of concepts to come to fruition.
Thank you, Armine. I think that those are really wise words, right? I mean, I think as we've been saying that I think the solution here is going to be a combination of these white boxes, black boxes into gray boxes. Try to incorporate what we already know and be assisted by artificial intelligence. Did any of the panelists want to add to that?
I just think it's so interesting that coming from, so I was living in like Silicon Valley, and there it's like, you have AI, yes, here's $100,000, here's like $10 million, like we want to fund you, even though they don't care anything else. But then in other industries, it's such a barrier, even the language we use, it's almost like we need to go on some sort of marketing campaign to be like, no, trust us, it's good. So it's just really interesting that you really have to kind of adapt your communication style to your audience. But yeah, I just wanted to comment on that. I really loved what you said.
That's interesting.
I also fully agree that it's not an either-or paradigm. It's not the way we currently do things, or some general intelligence that's off on its own. It's a mix. It's exactly right. There's a ton of technologies that have already been developed that are up there that have heritage and that work. And there's no reason to go and replace that with a neural network. And it's not going to do as well. Chances are. But it's trying to find these new challenges that haven't yet been solved by traditional approaches and that might not be solvable by traditional approaches. And that's where you focus your efforts and you work with the traditional approaches to produce a higher technology system. I think that's a great point.
And it's a good thing to be working on in Canada because we have a national pan-Canadian AI strategy. So at least within some areas, that term is liable to at least not get you kicked out of the room. But it's funny what you mentioned about computational intelligence, because I think the definition we discussed earlier was given because AI in its history goes through these AI winters where suddenly nobody wants to use that term anymore because the hype has exceeded the technological capability of what's actually out there.
I do have to say that the future looks bright in Canada for AI research. We've got companies like GlobeVision and NGC, and of course MDA and Mission Control that are using this routinely. And in fact, I think one of the signs of success here is that we as a space community maybe haven't even known, right? We've secretly sort of quietly put AI in there, and we've done it in a way that has kept people comfortable and is really making it seem a little bit more normal without, like we say, flipping the switch and everything's black box and nobody knows what's going on anymore. So I think maybe that's a sign, a really positive sign, a sign of the future here in Canada. So Mick, maybe you could speak to that.
That's exactly actually what I was going to pick up on. This is it a flipping of the switch? Is it a marketing thing? And I want to pick up on something Paul said, which kind of got me thinking. You talk about level 3 autonomy and driving reading a newspaper while driving down the highway with sort of this adaptive cruise control. And the weirdest thing about what you did in that example was show that someone actually still reads physical newspapers.
I know, I got to work on that one.
And that is a mentality shift. That's a marketing thing, right? And I wonder if we're sort of facing more of a marketing problem than we are like when we talk about adoption and barrier to adoption. What do we actually mean? Because there's clearly commercial companies that are just doing this because it is a better approach to solve the problems they have. And of course, commercial companies tend to have, a risk-reward equation that's different than government missions, because the incentives and the purpose of those missions are different, ultimately, at the end of the day, and where the money comes from, of course. So I guess my question is, are there truly barriers to adoption, or do we just need to keep doing this and eventually it just sort of dissipates? And or is there really a line that we need to eventually cross where there is this virtuous circle that starts to happen where requirements, of course, you're never going to have requirements that says thou shalt use AI. Why would you ever do that? But it's also a shift in mentality of what a space mission can be, or rather moving away even from a single mission paradigm to systems of systems where you have infrastructure in space that is long-lasting. Do we need to get to a point where there is this level of trust that we can start to think differently about how we explore and use space?
Yeah, great point. So, panel, what do you have to say about that one?
I could start. People keep telling me that there's going to be a lot of resistance to what I'm doing. They say, "Oh, good luck being director of AI at MDA." You've got a lot of people to convince, but I haven't met any of those people yet. Everyone is generally very supportive in the industry, and everyone has these really everyone's looking really far out to some really, really challenging problems. And I think there's a lot of excitement building. There's a lot of interest in what's going on in autonomous vehicles, in these large language models, in image generation. People are starting to see, what is possible. And I think there's I think it's very positive. I do get this impression from everyone I've met so far that, there is an interest in this, and there is, people who want to solve this together, who want to figure out how do we verify this and certify it for a flight. And so I keep hearing that I'm going to run into all this opposition, but it hasn't materialized yet. So we'll see.
That's good news. Hey, Kelsey, what have you found?
Yeah, I mean, I feel very fortunate that JPL is like very much into exploring for the sake of exploring. I mean, it's a very amazing place to be at and to research at. So I don't think any question that is a silly question or like too out there, especially for AI, being on the machine learning team there. And then the other side, I'm a PhD student in academia, so the whole point of academia, I think, is like to push boundaries and like to do ideas that have never come up with before. So I haven't felt too much pushback there. I think it's more when I'm looking at cases where I'm using like space-based data sets and Earth observation to inform policy in some way. Like, I'm very interested in humanitarian efforts and disaster response and these types of things. So there's more resistance, I feel like, in adopting technology in that way, because this is life or death for a lot of regions of the world, whether you're looking at landslides or floods or fires. And so if you're going to be relying on these types of technologies to make decisions that are going to inform whether or not a community gets the need that they absolutely need during different crises, then I think there's pushback there just in terms of like, this better work. And why does it work? And just more under the hood understanding of why your system works and proving where it does fail. And so again, I don't think it's a full replacement of the current systems that are in place for disaster preparedness in countries, but for a lot of countries, they don't have the same infrastructure that we do in Canada or in the US or in Europe. And so I think it's just really, again, just going back to talking to stakeholders and trying to inform them of what the power of these tools could be. And so that they can use them.
That marketing message that you brought up and Mick touched on too. Yeah, I think just framing it in the right way, and even Armine mentioned the same thing too. How do we phrase this? How do we get adoption? I think that's great. Did you have anything you wanted to add to that, Andrew?
It's always dangerous to take a question from your boss in front of a panel of strangers. I think there's a number of technical challenges that remain, but that we've made great strides in the last 10 years. So Earth observation example, 10 years ago, if you got the state-of-the-art ship detection software from Spaware, and it happened to be windy in the image you were looking at, you would detect a lot of white caps as ships. And so just in terms of computer vision, the strides we've made in technical challenges and that we've overcome has really shifted things dramatically. And for anybody who did like natural language processing in 1995 and compared to what's possible with a digital assistant right now, I think the technical progress has been so fast that some of the process pieces and adoption pieces now look like they're lagging, but that's only because the technology has really changed in the last 10 years. I think in the space front, it's interesting because, like Kelsey mentioned with constellations, if you have 200 satellites and one is down for 24 hours, it's very different than trying to convince somebody to do anything on James Webb Space Telescope, where you got one shot, it's a $10 billion mission, right? There's not going to be 200 James Webbs. So it's very context specific. But in the lunar example, if you look at what Starship's carrying capacity is, suddenly this mass requirement that has driven so many of our requirements generally falls. And what are you going to do? Like, what are you going to send? Because suddenly you can send a whole bunch more robots, and you actually have the people that would want to sit there all day, every day, managing a fleet of, hundreds, potentially thousands of robots. No, you'd want some level of autonomy. And whether that's teleoperations with a heads-up display that says, are you sure you want to drive into that crater? To, if you've got 2,000 of them, maybe you do want to drive into the crater just to see what's down there.
I think you touch on a really good point, Andrew, and that is how expansion in other aspects of space systems engineering is enabling growth in other areas. I think, Paul, you mentioned that 10, 20 years ago, nobody thought about doing machine learning because we had 386 computers, right? And it just wasn't possible, right? And now we got more up mass. Now, well, maybe we can send more more robots. Or now we can build things with 3D printing. Now we can build parts that we've never thought of before. So let's apply that to machine learning. Let's apply that to adaptive control and all these other things. So I think this, when somebody asks me, what's it like being an aerospace engineer, I'm saying it's amazing because we get to dabble in all these different disciplines, and an advance in one discipline means that we can do something else in another one, right? So it's a great place to work, right? And I think we're seeing that as particularly here with artificial intelligence. Do you have a comment here you wanted to make, some experiences you wanted to bring to the?
Actually, it was a curveball. I'm just trying to.
Sure, yeah. Curveballs are fun.
Curveballs are fun, right?
Yeah.
We talked about, and I'm saying we, but you guys talked about getting information from data with AI in general and machine learning. I was wondering, have you ever thought about, or even experienced, or think in the future might be, using AI and machine learning as a design tool? So just to know what is going to happen with that system or that sensor or something like that. Is this something even in the cards or something?
Love that. What do you think?
I personally haven't, but I do have a colleague that's working at the European Space Agency in sort of the natural language processing area with respect to looking at like old mission documentation and basically using an NLP to filter through that to kind of extract like the pieces that did work and the pieces that didn't based on the work of many hours of human hours of typing up, this is what didn't work, this is what failed, this is why, and sort of informing new designs that way. But that's all I can speak on that because I don't do that research, but I can happy to give you her name if you're interested.
Yeah, it's a hard yes for me. Basically, there's techniques that have been out there for some time, and they're actually used, I think, in the automotive industry. But I'll take an example from academia. You can design tables, for example, using machine learning. And so this is something that's been around for a while. You can design buildings like that conform to physics; they don't fall over. So you can have a physics simulation where you've got gravity and all that, and the materials are all simulated. And then you're actually just manipulating these designs in a machine learning space, and you evaluate them based on how strong they are, how long they last, whatever, and how you can even have a human in the loop evaluating their aesthetics. Do you find this visually pleasing? And then over time, they can actually learn a visually pleasing building that's going to last a long time. And so these techniques exist, and I think yes, we will bring them into the space industry.
Yeah, I think that's the crossover between topology optimization and artificial intelligence, right? And I think you brought this up too, Paul. You're saying that so many people think artificial intelligence means neural networks, but it means so many different things. It means it means linear regression, it means classification, but it also means things like topology optimization. So I think that's a great point. Did you have anything you wanted to add?
So there is already a launch company that's 3D printing rocket parts that's using AI to iteratively increase the quality of its manufacturing design. And it does come up in really interesting ways. So a couple of weeks ago, you might know DeepMind that came up with this AlphaGo reinforcement learning algorithm that plays Go. And they've since done that for protein folding with AlphaFold. But the latest thing they've done is they asked it to do better matrix multiplication and set it up a game where it's cracked an algorithm that was the best way to multiply matrices for the last 50 years. And I sent this paper to my team, and you've never seen so many people excited about multiplying numbers together. Because as part of the software engineering process, doing large-scale matrix multiplications on space hardware is one of the bottlenecks for us. And so that was a completely unexpected way for AI to get into our kind of software engineering manufacturing process. And for us all to have a very good Friday, being like, this paper is so amazing.
And that's one of the things that I love the most about this is the excitement that it creates, right? I mean, we can all get excited about every aspect of space systems engineering, everything, but I think the potential that we're seeing with artificial intelligence that we've already seen is so exciting. I mean, it makes for great Fridays. We talk about multiplying numbers. Who gets that excited about numbers? But of course, we all do. So, thank you. Did you have a comment you want to add here?
Just a comment. I think one of the reasons that AI gets a bad rap sometimes is AI is used ubiquitously. So, as an angel investor looking at companies that come in, to your point earlier, I see every company being AI enabled. I think there was a garbage truck application that came in, and they were looking for $250,000, but they were AI enabled, and I'm scratching my head saying, no, you're just a camera. So how do we, particularly as a layman, how do I challenge people who claim to be AI enabled and really aren't? Because ultimately, I think if we label everything as AI, the ones that fail or don't produce the results that are expected are going to give the results that you folks are doing a really bad name.
That's a really good point. I think this comes back down to this marketing idea. So it's almost like a catch-22. Yeah, you're right, Paul, that a lot of things that we're doing already is AI, but how do we phrase that in a way that keeps us in the right direction? Anybody have anything you want to add to that?
Yeah, so there's a problem with incentive structures, right? If you add the right thing and your valuation doubles, but you didn't actually do anything but add the right set of letters to your business plan, then that's a problem. And I think there's a study that said that 60% of companies that claim to be doing AI are not doing AI of any form. And so I think what's exciting about the space industry is instead of looking at what the solution is claiming, look at the problem space. Is there actually a need at any level for more autonomy, or is a camera just fine? And in space, the need for autonomy is very clear. Like the bandwidth constraints, the environment that you can't plan for, in all different verticals, space domain awareness, Earth observation, planetary exploration, there's an autonomy problem that would allow you to get more capability if you were able to add a little bit more intelligence on board. And so that's why, at least in the space industry, it makes sense to be talking about this.
Yeah, I think that's a good point.
Yeah, I
Anything else,
100% agree. I mean, when we were, our last commissioning for Planet was in January of last year. And I was the lead on that with a colleague of mine from Berlin. And we had fully autonomous commissioning campaign for 48 satellites. So we launched them. After that, we didn't have to do anything. They were able to detumble, nadir pointing, fold out solar panels, everything, get it all ready to start taking images. And that was completely autonomous, so that we could actually still focus on the other 150, 180 satellites that we already had to deal with. So I think for space, Andrew made a great point, it is pretty primed for autonomy and to harness autonomy effectively. But how do you spot hey, is this AI or not? I think it's just asking questions, truly. Because, if, like you said, oh, it's just a camera, then yeah, I think you clearly understand the problem space enough to be like, this doesn't seem like AI to me, maybe. So I think it's just asking the questions as well to figure out if it actually is what you think it is, because yeah, I think AI is unfortunately thrown out a lot to be sort of this umbrella term that maybe it's not really truly AI for a lot of cases. So I think it's just really asking questions and keeping that dialogue open.
Yeah, I think it's a mix sort of I mean, especially in the space industry, I think it's autonomy. It's not necessarily AI, it's autonomy. And autonomy has existed long before sort of neural networks. And autonomy will be a mix of current approaches, manually derived approaches with neural networks. And so on the one hand, it's autonomy. It's not necessarily AI. We can just call it autonomy. These are autonomous systems. And there's a very clear definition there, whereas AI is extremely vague, as everyone has already mentioned. And on the other side, if you want to know something specific, then yeah, get into the details. What is your data set? What is your model? What is your learning algorithm? Tell me how this is machine learning, not necessarily AI, but what is this machine learning? How is it learning? And get into that discussion and figure that part out. And then, it's just because you're just using the camera, maybe it's not machine learning, it still might be autonomy, it still might be some sort of autonomous system. And there's nothing wrong with that. There's no reason that shouldn't be any less worthy of investment just because they use a different term.
Yeah, I think that's a good point. So I think we've got time for probably one more comment. So if you'd like to ask our panel.
Hi,
that'd be great.
Mark Angelillo, CSA Gateway. Hi, Paul. We're probably going to rub elbows at some point.
Looking forward to it.
Yeah, so you talked a lot about, there's been rovers mentioned and your robot in a room full of stairs, and you talked about the sim to real domain transfer, the difficulties and challenges. I think we have a pretty good opportunity on Gateway, potentially a 15-year mission with an AI-enabled robot, right? But I wonder if you could expand on your views on the challenge of commissioning. And we have an 8.5 meter long robotic arm in 0G, and you can't really have that in a room on Earth to train it, right? Rovers, you can have a simulant environment and train it that way, maybe perhaps more easily. I don't know. I'm just wondering if you can expand on that challenge and how maybe
Sure.
the opportunity?
Yeah, great question. So there's a mix of solutions here, and a challenge as big as Gateway and C3 requires sort of you kind of go and try everything, and you use all of the techniques that are available. And so one again comes back to simulation. Yes, it's very difficult to in real hardware simulate 0G, but you can certainly simulate that in an advanced gaming engine, and there are some really advanced high fidelity, high speed physics and dynamic simulators now that weren't even around 5 years ago that you can then build into these simulators. And then so you can actually do a very good job of recreating within a computer simulation the expected environment that's going to be out there. But of course, it's not going to be perfect, and there's going to have to be iterations. So you also have very high fidelity mathematical models that you build, and you can validate those on hardware sort of in pieces. But there actually, there actually are ways to actually build robotic systems on Earth with simulated 0G. You can do sort of weight balancing, and this is something that is done at MDA, where you actually can counteract the sort of gravity using mechanical systems, and you can actually simulate some of these operations in 0G, and you can simulate a lot of these other environments. But it's difficult to piece it all together. So you can maybe simulate 0G, but then at the same time, it's also hard to simulate radiation or temperature fluctuations or all that. So then it comes down to, again, trying to characterize the range of variables that you're going to hopefully see up there, and then try and build a system that is general enough to handle all of those. And then obviously there's this commissioning phase when you actually get up there and you have this system, and you can start recording real data, and then try and then take that data and use it to augment your simulations and your hardware systems on Earth to then have a higher fidelity environment for then additional training. So it's going to be a big challenge, but most of the technology I would say is already there. The key piece is that final validation step, that commissioning step, where you actually get there and collect that real data and use it to validate the models. And just to add to that, it doesn't matter if up until that point the model that you've built doesn't work. You've got this pipeline now. You've got this simulation environment. You've got this hardware testing. You've got the model training. All you do is you adjust all of that with the new data from Gateway, and you just run it again. It's not like you have to spend years building every piece again once you have that new data. You just adjust a few parameters, hit go on your training regiment, and then hopefully, all things, fingers crossed, and everything kind of pans out. So it's not like when you get up there, you have to reinvent the wheel all over again. You can prepare your pipeline, and so that when you have this new data, you just run the pipeline again.
I think that's great, and I think it's a good thing to remember here too. Is at the end of the day, we are talking about systems that can change over time, right? And so we're not locked into a piece of hardware that we just built that we have to live with for the next 10 years. So in the interest of time, maybe we'll just take a quick 2 minutes to wrap this up. And what I'd like to ask each one of you, and I was inspired by Paul, you made the comment that you predicted to your wife what driving was going to look like in 5 years from now, and you were horribly wrong. So let's put all of you on the spot. I want to have a quick, like a 15-second prediction of where we're going to be in AI in space 15 years from now. So Andrew, we'll start with you. Where are we going to be?
Ooh. So I think right now we have an Earth-centric view where all of our computation and all of our data is coming back to a ground station on Earth. If you look at the Global Exploration Roadmap, which has 27 countries signed up for the kind of path from Earth to Moon to Mars, at some point, much like using water on the Moon to make rocket fuel, you'll start processing the data closer to where it is, because the 1 over squared law for your communications is just going to make that way more efficient to do. And so I'm not going to hazard a guess on anything more general than that, but we do, like right now we have an R&D project with ESA where we're looking at federated learning approaches where you don't send the data back to Earth, but you have a system of robotics on another planet using a computer vision model, and they're updating the weights across a distributed system. And so
I like that. So in situ analysis, that's good. Kelsey, what's your prediction?
That was sort of mine, but basically I think...
All right. Well, there's consensus. That's good. I like
yeah,
it.
I think really just the amount of onboard decision making is going to dramatically increase, whether that be for rovers, satellites, probes, what have you. I think just because especially when we have missions that are going to things like Europa and Enceladus, these like really far away planetary bodies, having AI-enabled decision-making on board for things, especially with respect to science return, I think is going to dramatically increase, and that's going to result in, I think, better science and more science from these missions than we've ever seen before.
Fantastic, good. And Paul, we're going to hold you to it now. Your wife is listening.
Yeah, well, she's smiling right now because I'm going to say the same thing I said 10 years ago. But again, this is a personal opinion. I'm not, in this case, representing the MDA, but I do think in 15 years we will have level 4 autonomy on board these systems. So the compute will get there. And it's actually easier in many ways for level 4 autonomy for space systems than it is for driving a car. There's not many pedestrians on the moon yet. There's no cyclists on the moon. There's no weather. There's, even maybe Mars you have some weather, but there's not a lot of these things that we have to grapple with here on Earth. And so I actually think the science is already there to get level 4 autonomy onto these systems. I just think it's an engineering problem at this point. And so to me, it's just a matter of time. And the difference between level 4 and level 5, by the way, I never fully got into that, is level 4 means there's certain edge cases where the system will disengage. Level 5 is true autonomy. It's like human level or above, where you can adapt to never before seen scenarios. Let's say you've never skied before, but you can put on a set of skis and you can make your way down the hill. That is still a science problem. We haven't gotten the technology to a point, the science to a point where we can achieve level 5 autonomy. But I think level 4 autonomy is possible, and now it's purely an engineering problem.
I love it. I think the future's bright. I want to thank everybody here for this conversation. It's been really a lot of fun, and I want to especially thank our panelists here for the perspectives that you've brought and all the participation today. So let's finish up the conference with some great conversations and our Turnbull lecture a little bit later. And thanks for your time today. We'll thank the panelists. Keeping things just before we head out, so I'll turn it over to you. Thank you.
Yeah, keep the house.
Keep the house.
Thanks, Andrew. Kelsey, thank you. So just before everybody breaks for much needed coffee or tea, I just want to say that we have 2 breakouts now, not 3. One of them is in the concerto all the way down the hall. The other one is right in this corner here. I think that the coffee will be, it's available right now. I checked outside, so it's fresh. One thought that Andrew leaves me with is the distinction between autonomy and artificial intelligence. And Andrew messed everything up, Paul, right at the end by talking about level 4, level 5 autonomy as almost like the next level of artificial intelligence as we're moving up the scale, and AI now is no longer level 3 autonomy. AI has to be like level 5 autonomy because level 4 autonomy is already autonomous. So the artificial intelligence part has to be beyond that. Anyway, it's a very interesting conversation. I really appreciate the panel for raising these very interesting issues, some of them even philosophical. So thanks, everybody. Enjoy coffee and technical presentations, and then back here at noon for the Turnbull lecture.